lecture of today by Lance, continuing his discussion.
Thanks a lot. So any questions from last time? Okay, today's going to be a whirlwind tour, as usual, with last lectures in a series. Last time we discussed the symbol. I showed you how to calculate the symbol of some simple classical polylogs, one of which was the symbol of the dilogarithm of x. We showed that it was -1 times this rank 2 tensor. And then if you plug in 1 minus 1 over u, which appeared in the one loop, finite part of the one loop amplitude for the form factor, you get, just inserting x equals 1 minus 1 over u into this formula, you get this one. The symbol involves these are implicitly logarithms, so the log of 1 over u is minus the log of u, and you can separate it out like this. So you see you have symbol letters. The letters are in this expression are u and 1 minus u. But this was just one term. There was also v and w that are related by a cyclic symmetry that rotates u, v, and w. So the symbol alphabet for the 3-point form factor that you see at one loop is this. And about 10 years ago, it was calculated at 2 loops. And so this symbol alphabet works at 1 loop and at 2 loops. The 2-loop one was Brandhuber, Travellini, and Young, 1201-4170. Actually, just before that, there was a calculation by German, Glover, Yakie, and Koukoutsakis. So they did QCD, and they did planar n equals 4. And so one loop is weight 2, symbols of length 2. The weight 4 result was the entire answer for the planar n equals 4 term. And it was only a piece of the QCD term. But they coincided, which is kind of amusing. They were the same function. And the symbol, if you wrote out the symbol for the weight for the remainder function at 2 loops for the 3-point, that symbol has like 84 terms. We'll see there's a much simpler way of writing it that will knock it down to just 12 terms. So also remember from last time, we had a way of the way we describe the derivative of any function. It was a sum over the letters in the symbol alphabet of lower weight functions that are also these same iterated integrals times d log of the SKs. We can also apply this relation once more. If we apply it all the way down to the end, we get the symbol. But these we call the n minus 1, comma 1 coproducts. Because they have weight n minus 1, and we've like peeled off one logarithm. Sometimes we call them the single coproducts. But if we do this one more time by taking the differential of f of sk, we get to use the same formula. So we expand it over the set of symbol letters, d log, And now we get a second index because this sk just kind of belongs to the function, and then we put a sj in front of it. And so these things are called the n minus 1, n minus 2, comma 1, comma 1 coproducts. Or double coproducts. But they're not all independent because there's a relation which abstractly is d squared f equals 0. That is a differential, d squared is always 0. And what this really means in practice is that mixed partial derivatives are equal. And in our case, we have only two underlying variables, and we have to impose this equation. And this will lead to, so we call this equation integrability, and it's not the same as integrability as used in the physics terminology. It's just the integrability of functions, that we can integrate up the first derivatives consistently to get a single function. And there's no condition until you get to at least two underlying variables. So if you're on a one-dimensional line, there's no integrability constraint. But here there is one. Let's first take this equation here and convert it into a derivative instead of a differential with respect to one of our two underlying variables, u. And let's sum over the symbol alphabet over here. And let's remember that 1 minus w is u plus v. And w is 1 minus u minus v. So we need to keep the terms, the SKs that depend on u. So we won't need the ones that are v and 1 minus v, but we'll need the other 4. So this equation just tells us that the derivative of any function in the space is fu over u minus fw over 1 minus u minus v minus f1 minus u plus f of 1 minus w over u plus v. Call that equation 1. Does everybody see how I got that? I just took the logarithm of these 6 letters after substituting for w, and I took the derivative of the logarithm with respect to u. So the v and 1 minus v is an independent variable. I'm holding it fixed, so I don't get any contribution from them, but the other 4 depend on u linearly. And so I take the derivative of those logs, and I just get 1 over something with a minus sign if there was a minus in there. But I could do the same thing with respect to v. And it's the same formula, except the roles of u and v have been exchanged. So call that equation 2. So now we just want to derive integrability relations by taking the 0 is equal to the v derivative of equation 1 for the u derivative minus the u derivative of equation 2. So that will have terms in it like I take equation 1. On the right-hand side, I differentiate with respect to v. I get a 1 over u, that comes out front, but then I need to take the v derivative of this. And I can use this formula again, but I have to remember it's for fu, not for f. So I have to put a comma u on everything. So I get fv u over v minus fw over 1 minus u minus v. Okay, so that was the derivative of the first term. And then there's a second term, which actually has two contributions. It has a plus 1 over u minus v squared fw. And then it has a minus 1 over u minus v times the same kind of expression as this, except comma u gets mapped into comma w, because there's a w here and there was a u there. So there's a bunch more terms. Okay, so you actually get quite a few different terms when you do this, and you need to set the whole thing to 0. And all of these f double things, they are logarithmic integrals. They kind of vary logarithmically. And they have rational prefactors. And there are no identities between the rational prefactors and the logarithmic stuff. So you need to set all the rational coefficients of any independent rational prefactor has to be set to 0. And so, you know, there's a lot more terms here. But we might be able to identify one contribution, for example, by noticing what happens if we take u and v both towards 1. Then this term is singular, and that's the only singular term there. And this term is also singular. When we go through these terms, there's a term that comes from differentiating this thing with respect to v, and there's a piece of it that has a f of 1 minus v then sitting in front of the 1 minus u, and it has a factor of 1 minus u and a 1 minus v in it when you go look at the contributions. And then there's another term from the exchange of u and v. So there's a bunch of other terms, but they're all less singular when we take u and v towards 1, because this blows up like, you know, two singular powers of 1 minus v and 1 minus u. And all these f's, they're slowly varying logarithmically. So that tells us that one of the equations we're going to get is f 1 minus u 1 minus v minus f 1 minus v 1 minus u equals 0. So this is one of the consequences of solving these equations. You can solve them more generally. It's a little messy, but this is one of the orbits, because I can also cycle this guy. I can use the dihedral symmetry that the whole system has to find two more equations. Now, and so there are three equations like this. The maximal size of a dihedral orbit, since it has cycles and flips, would be 6. But this guy is symmetric, or really antisymmetric, under exchange of u and v. And so the flip doesn't do anything. But if you cycle, you'll get two more equations. And then the next one takes a little more analysis to find, but it's actually, let me write some notation, because the integrability equations always involve antisymmetric combinations. So because of this fact that we're taking the difference of two different orders. So let me define with a kind of commutator notation the difference of f xy minus f of yx. So this would just be written then as f of 1 minus u 1 minus v equals 0. And then there's one other equation, which is f of u comma v plus f of 1 minus w v equals 0, plus dihedral images of this equation. And in this case, this guy's a little more asymmetric, so there are 6 equations of this type and 3 equations of this type. So there's a total of 9 separate constraints on the functions, double coproducts, from this from the fact that they're just that they have to be consistent functions. Any questions about that? By the way, this space is sometimes called two-dimensional harmonic polylogs. And it goes back to German and Remedi. Around 2000. It's a generalization of another space called 1D harmonic polylogs, which was by Remedi and Vermazerin. And that's similar to the one we talked about before with the G of AIs, where the AIs just belong to 0 and 1. Or they could actually be -1. So those are 2 kind of famous function spaces in the physics literature. Any questions? So whenever we have multiple variables, we get a bunch of linear relations. Yep. No, sometimes it changes. Here you get lucky. But sometimes there are more complicated functions that show up at the 2-loop level. Maybe just because I'll give you an example, because I'm not going to have a whole lot of time to get to it later. But in the 6-gluon case, there's an alphabet which has variables which look very similar, and the dihedral symmetry looks very similar to the form factors. But in fact, this thing is not a ratio like S12 over S123. It's actually a double ratio, which involves some other invariants in the 6-point case. And the reason it's a double ratio is a secret symmetry, which I mentioned, but I won't really have time to talk about, called dual conformal symmetry. So anyway, these are like 6-point integrals. And when you do some of these integrals in 4 dimensions, which you do for the 1-loop case, you find 6 letters which look exactly like these formally, except they kind of have hats on them. But then when you go to 2 loops, and actually you can actually go halfway to 2 loops if you evaluate this scalar hexagon in D equals 6. It's a weight 3, it has a weight 3 symbol, and it actually enters the derivatives of interesting 2-loop integrals. So it's an important function. So there are certain 2-loop integrals, which your chair wrote an important paper on, that have certain numerators. So we call this omega 2. And they more or less look like, let's call this thing phi. So omega 2, the symbol of it is like the symbol of this phi tensored with some new letters involving y's. So there are 3 more new letters. And you don't really see them when you look at the 1-loop amplitude. You only start to see them at 2 loops. And then it stabilizes. But there can be even worse cases where you see new letters at 3 loops. So the 8-point amplitude, you don't see all the letters at 2 loops, you see more and more. Also, which letters you see depend on which helicity configurations you're in, especially in these larger number of points. Great question. I showed you this I'm working on, I gave this example because it's the simplest, but it's generally a lot richer than that. Any other questions? So I also want to point out that you can map from one alphabet to another alphabet. Suppose we take the logarithms of the SKs and we change them to some other alphabet, SK prime, which is a sum over some AKJ times the original logarithm of SK. So this would be summed over SJ. J equals 1 to the cardinality, number of elements in the alphabet. If we make a change of basis like this and it's invertible, then that's gives us an equivalent alphabet. And in principle, you can use any alphabet you want, but some things become more apparent if you pick the right alphabet. So actually, since I mentioned this, I might as well point out that we found a better alphabet here, which was to change these guys into U hat over V hat W hat. And these are related by cyclic permutations. And the important thing is that when you work this out, it has only one of these 3 particle invariants, the things that appear in the denominator here. And then it also has some rational function of the SI, of the 2 particle invariants. But it isolates a single 3 particle invariant. And then we use cyclic symmetry to define, because there's the same dihedral invariance, to define C and W, B and C. And there was also another, at the same time, it was also useful to define something like, this is a smaller modification, but it's very useful to write D hat, E hat, and F hat. Anyway, we had some good reasons for writing these down. They made some causality properties in the 6-gluon case more manifest. There's a story I won't have time to go through in general, but when you have a multi-point amplitude, there are constraints on how you can cut it twice. And the constraints really are applicable when the cuts separate 3 particles at a time. So at 6 points, you can have a cut that puts 3 particles on one side and 3 on the other. And there's a incompatibility of the cuts in the channel. For example, this first cut here gives a discontinuity in the channel S234. And this one gives a discontinuity in the channel, this other cut, I guess it's 345. And a long time ago, Steinman, 1960, argued that the 6, more generally than that, but this kind of double discontinuity should vanish. And these discontinuities are related to, are captured by the symbols, by which letters you have. And when you can isolate the 3 particle invariants into single letters, you can translate this into an argument that you should never have A hat and B hat next to each other. So you write down the symbol and you never see A hat and B hat next to each other. And there's other ones related with C hat and stuff by dihedral symmetry. So when we started to work on the form factor, we knew about this. We didn't have as good a causal reason to do it, but we just thought, it would be a good idea to try this. And so we defined, now without hats, in the form factor context, the same exact transformation. And so we make this change of variables here on the form factor side with no hats. So this is all the 6 gluon. And that was just an aside. But it motivated us to, in the form factor F3, make this change of variables. And if you have conditions that are written up here in the old alphabet, you have to transform them to the new alphabet. And it's not so hard to do. If you go back to the defining relation and match the differentials. So if you now change to this new alphabet, so we're going to have an L3 prime, which is A, B, C, D, E, F. So if the you sum over L3 prime and write down the same formula, and then here you plug in log A is equal to log U minus log V minus log W, and you go, etc., and you go collect all the log U's. That will tell you what FU is, and you find that it's, and also F1 minus U is actually just the same as FD. So these relations tell you how to map from one alphabet to the other. And when you plug them in there to these double differential relations, you find that they become those integrability relations. So, including dihedral images, there are 3 of these and 3 of these. And then there's two more here. And then the last one is more complicated. Something like that. So actually, this one looks a little weird, because these you get all dihedral images. This set here, if you dihedrali permute, I'm going to make a little mnemonic here, which is D, E, F. A, B, C. So this figure has a dihedral symmetry. And so it reminds you what the dihedral transformations are. If you cycle this figure around, it takes D to E to F. And that's like taking U to V to W. But at the same time, it rotates A, B, and C. Or you can flip it around any corner of the triangle. And those remind you what the flip transformations are. So the dihedral symmetry is sort of manifest in these 8. And this one looks a little weird because D goes to E, B goes to C, and then goes to F and A. So that cycles, and this cycles, but then this one looks like it doesn't cycle properly. So what's going on? Anybody know how it works? It looks a little weird that it doesn't cycle into itself. Well, it's okay because when I cycle this, I get C comma A. But then I go look up here and I see that this equation tells me that C comma A is the same as B comma C. So it's actually okay. The system is dihedrali invariant, but I can't write it in a way that every single equation is dihedrali invariant. Okay, so these are just the integrability relations. But then you start looking at some low loop answers and you discover certain patterns. And well, let me first write down, when we use this alphabet, the one loop answer, I should ask if there are any questions about that. Yep. Sort of. It isolates S123s in the 6-gluon problem. And it was motivated by the 6-gluon problem, but it doesn't directly have any reason to do anything good. But then you do it and you see some good things happen. And then later on, we understood, and I'll talk about this at the conference next week, this symmetry called Antipodal Duality, which relates exactly these two problems, the 6-gluon problem and this form factor problem. And so now our sort of way of understanding the good things that happen in the form factor is because of this relation. We don't understand this antipodal duality relation, but it maps causal constraints from non-overlapping cuts to empirically observed constraints on the other side. So we still don't understand why the symmetry holds, but at least it gives us a way of kind of understanding the good things that happen. Any other questions? Now, at one loop, the things that happen, well, the symbol has this form, and it's can be written as -1 times the letter B tensor with the letter D plus dihedral. And that gives 6 terms, because this thing is not invariant under any flips, so it sweeps out 6 terms. I won't write them all down. The 2-loop guy becomes 4B tensor D tensor D tensor D plus 2B tensor B tensor B, whoops, tensor D plus dihedral. And that's a total of 12 terms. Later on, when we got to the, and so this was basically worked out by Brandhuber, Travellini, and Young, except in their sort of basis, they got 84 terms. And some of the improvement was by switching from the remainder function to this E function, as we described last time, different normalization. And then some of it came from switching to this different alphabet. So this one has 636 terms. So I could spend the rest of the hour writing them out, but I'm not going to. So it's not quite as simple, but it still has a lot of patterns in it. And one of the amazing patterns is that, so these integrability relations are 9 relations, and they're antisymmetric in the exchange of the 2 slots. But it turns out that these symbols all obey another condition where you take the simplest guys over there and you improve them to say that the symmetric part, or just the either ordering vanishes. Since the antisymmetric part vanishes, if I say that it vanishes with one ordering, it's like saying the symmetric part vanishes. So there are 6 more relations here. So it's an empirical observation that in this alphabet, well, it would be true in other alphabets too, but we didn't really notice it, that there are only, that there are actually 9 plus 6 or 15 constraints. On the double coproducts f of x, y. Now, how many double coproducts are there? Well, there are 6 letters times 6 for each slot. There are 36. That's the naive number, but then we subtract these 15 equations, and we say that there are 21 independent pairs out of the 36. So that's sort of a structural feature of the space, which is a much smaller space than the space of 2D HPLs, based on this empirical observation, which we really only noticed we noticed some of it at about 3 loops and the rest of it around 5 loops or so. So it takes a little while. Interestingly, some of this is also obeyed, a piece of this is obeyed by QCD or general 2-loop integrals with the same topology. And because it's obeyed by all of them, it tells you something about QCD. For example, this planar integral and some non-planar integrals, they also, if you just look at the results for them computed by German and Remedi, they also obey this relation, but not this one. We don't know. Don't know for sure what will happen when the complete set of 3-loop integrals is known. Someone here is working on that, Juan Lim, I think, and there's some partial results already available. So, okay. Now, another thing to notice about these formulas, now there's dihedral invariance that rotates B into A and C. But the first entry, even if you start applying dihedral symmetry to these formulas, the dihedral to get the other terms, the first entry is always A, B, or C. And it's never D, E, or F. And this is one thing we do understand based on causality. So if we have a picture where a Higgs comes in and decays to some gluons, there can be a discontinuity that opens up when S12 is greater than 0. If it's less than 0, then maybe it's not really Higgs decay to 3 gluons, it's glue Higgs goes to glue glue. But as you switch the energy or move from negative energy to positive energy, move this into the final state, this guy opens up, and then there's a imaginary part from unitarity, as Yara was describing. So there's a branch cut at S12 equals 0. But by symmetry, there's one at SII plus 1 equals 0, cyclically mod 3. There's also a branch cut that opens up that happens at S1, 2, 3 equals 0. If we look at U, V, and W, because they're ratios of these, the branch cuts are all located when U, V, and W are at 0 or infinity. But the first entry of the symbol, in the symbol, the branch cuts are characterized by the vanishing loci of first entries. Like in the polylogarithms, the LINs, they had the symbol 1 minus x tensor x, and the branch cut was at x equals 1. So it's at this vanishing loci. So these guys can go in the first entry. U, V, and W are allowed in the first entry, but 1 minus U, 1 minus V, 1 minus W are not. Okay, but A, B, and C are just rational combinations of U, V, and W, so they're okay. So that explains why they can be there, whereas D has a 1 minus U in it, so you can't be there. Okay? So we understand why these two formulas only have A, B's, and C's in the front. But there's also a last entry condition, which is empirical, and that's that EA, EB, and EC are 0. So this EA means clip off the last entry, A. And it's always 0 because the dihedral images only rotate D into E and F. You never see an A in the last slot in either the 1 loop or the 2 loop formulas. So we call these final entry conditions. And we are motivated to look for them because there was a physical reason for them in the hexagon case, which was some differential relation called the Q-bar equation. So in the 6-gluon case, there are analogous conditions from the Q-bar equation, which is due to Simon Caronhua and maybe and Song. But we just use that as a license to look for them and then impose them to go to higher loops if we see them. So these are kind of empirical, but we can also use them to help with the bootstrap. Now there's one other condition that you have to impose. These branch cut conditions, there is actually a subtlety in the present case. There's another way to develop bad branch cuts. So in this case, there's one more implication of the branch cut conditions, and it's when you take one of these, and I'm phrasing it back in the old alphabet. It's just a little simpler to state. If you take U to 1 and V and W both towards 0 from different angles, you find that in order to avoid a branch cut at U equals 1, you have to, you could also do this with the D because it's the same thing. FD is equal to F1 minus U. You have to impose this constraint too. And that knocks out some functions and even some symbols. So the net result is that we have some picture of this space. It's graded by the weight. So down here at the bottom, there's the weight 0 function 1. And then at weight 1, there's log u, log v, and log w. And those are the only first entries. That actually means that the derivatives of the weight 2 functions should drop onto these logarithms. And when you go through and construct them, you get, I'll just change u, v, and w to u1, u2, and u3, so I can write weight 2 more compactly. Now, so that's at weight 2, at weight 1 there are 3 functions. And at weight 2 there are 9 functions. There are 3 times 3 here. At weight 3 there are 21 plus something that doesn't have a symbol, zeta 3, a constant. And they include Li3 of 1 minus 1 over ui, but they also include stuff that truly depends on multiple variables for the first time. So these guys also show up. And then you can keep constructing this space. And you can do it all using these kinds of double coproduct relations. So you try to write an ansatz for a function at the next weight up by using linear combinations of the ones at one lower weight. And then you sort of take their derivatives or compute the double coproducts, and you get linear constraints on the functions. Let's just give a simple example of that at weight 2. At weight 2, suppose the second letter is A, B, or C. And we know the first letter cannot be D, E, or F. And now we've said the second letter is not D, E, or F. If we look at this relation here, and we kill everything that has a D, E, or F, we just get the last term. And we learn that FBC should be 0. And then we go up above and we learn that FAB and FCA should be 0 too. So if the second letter is A, B, or C, then A, B, and C are sort of like independent things. Remember that the symbol of log x, log y was x tensor y plus y tensor x. That obeys this relation that has the property that fxy is equal to fyx. So we've learned from this analysis that we can have any function of log A, B, and C of weight 2. So that includes log squared of A and log A, log B, plus cyclic. So there are 6 functions of this type. Now suppose the second letter is not A, B, or C. We could take it to be D. Well, what can sit in front of D in the symbol? We're not allowed to put A there, but we could put, there's one other, the second letter is D. We go up there and look at this longest relation again, and the ones that end in D, which come from twisting these around, have B and C equal. So it forces us to have a B. A is disallowed by the upper equation, but we can have B tensor D, but they're coupled together. And so you get this function here, this symbol. I leave it as an exercise to show that this is proportional to the dialogue we've seen before that has this symbol. Okay, so we recover that function, and there are 3 of those. And if we put that together, 6 and 3, we get 9. And so you can show easily in your spare time, reproduce, that by using these integrability conditions, you get these 9 guys. And to go beyond that at weight 3, you pretty much have to start putting it on the computer and solving these equations on the computer. So just like Henrik, we can get large systems of linear equations and unknown parameters, both in constructing the space and then trying to construct solutions for the amplitudes within the space. So any questions on that? Yep.
How do you know that there are no functions like a constant of weight 1 times
Yeah. One is sort of because the constants, I mean, there can be those constants at specific values, but whether they should be free elements in our basis, we know that when we evaluate a lot of, I probably should have also written this kinematic plane before. I think I showed it once before, but anyway, this is the whole kinematic plane. And there are various lines where the symbol alphabet collapses to things which give us these G's with special values. And when you take U to 1, you get multiple zeta values. And so based on that, we believe that the intrinsic free constants that you can add are always multiple zeta values. And I mean ones where you have nested sums and no signs in the numerator. And there's nothing at weight 1. There is actually, at weight 2, there's pi squared over 6. That's the Riemann zeta value, zeta 2. And this could be added here, but we actually found that it's like absorbed into one of these functions. And so we didn't need to add it as an independent constant. But actually in this case, everywhere above this, we also add zeta 3. I mentioned that here. And we add zeta 4 up here, zeta 5, zeta 2, zeta 3, multiple zeta values, irreducible ones when we get high enough weight. Good question. Yeah, once we add one of these, we also add a whole tower, but it's kind of trivial because it's like the previous tower, just multiplied by that zeta value. And so there are far fewer of those because the effective weight is kind of lower. So yeah, we have to add all those. And then we have to fix all those coefficients. When we work at the symbol level, those things, we don't count them. We throw them out. But then we come back again after we fix the symbol, and we can actually fix all these constants. Because these derivative relations, they hold at both symbol level and function level. And the only difference is you got to specify boundary conditions when you integrate them at function level. And so we pick a particular point here where everything is MZVs. And also there are singular logarithms in V and in W because those are both going to 0 here. So let me show you another So basically, whenever we're able, this is not going in exactly the right order, but whenever we do get a unique result for an amplitude and cross-check it, the first thing we do is we take its derivative using these coproduct relations. And in principle, the first coproduct could give us 6 different functions, which we would call EA, EB, EC, ED, EF. But we already know where the EA, EB, and EC are going to give us 0. And so we know that there are really only 3 independent first coproducts. But we can keep differentiating those guys too, and we can build up the following table of dimensions. So on the horizontal axis, we're going to put the weight. And it will 0, 1, 2, 3, 4, 5, 6, 7, something like that. And then here we'll put the loop order. L equals 1, 2, 3, 4, 5, 6. And then at weight 0, there's always just one function. And at weight 1, there are these 3 logarithms. Maybe I'll wait on that one for a second. And then at weight 2, as I mentioned before, there are 9. But when we start working at a fixed loop order, don't necessarily see everything all at the same time. So we see, okay, so the fact that EA equals EB the fact that these 3 are gone, and there are only 3 independent first coproducts, ED, EE, and EF. That's reflected by this number 3 here. So we go to 2 loops. The answer is weight 4. We take derivatives to get something weight 3. We count how many there are, and there are 3. And then we take another derivative of those 3 things, or take their coproducts more officially, and we count how many are linearly independent, and we find there are 6. And then we do the same thing at 3 loops, and we find that that 6 is still the same. And then get 21 here. So these blue numbers are meant to indicate that things have saturated in a certain sense, and the red numbers mean they've saturated in another sense. The red numbers mean we've explored all the different functions in this space, and it's stable. Sometimes we don't know what the space is, and we build it from the bottom up using these relations we were just discussing, and we get larger numbers than when we come down. So if we get too big a number, we go look for a rule in order to make it smaller. And also there are some numbers in the middle that aren't yet saturated. I forget what this one is. Anyway, so, but then we also do the same thing on this side. And the fact that these numbers are all stable tells us that we can predict the number of final entries, and we can build rules or equations that are analogs of these, but at higher numbers of final entries. So the fact that there are only 6 of these tells us some new relations. And the basic new relation is that EBF is equal to EBD, plus, of course, dihedral images, which would be 3 more. So, so we get this structural information at the end. We can, speaking of the end, it looks like my end is approaching here, the end of space-time, so to speak. So we're able to construct these trimmed-down spaces and find the amplitudes inside them. And of course, I really ran out of time because I didn't really tell you a lot about all the usage of the boundary value information, but it all comes back to this, this graph again. So let me at least explain that part, and then I'll stop. These variables here, if we take like this one here, this segment here is v equals 0. So if we take P2 and make it parallel to P3, so we go into a collinear limit, then these, if we do Higgs to GGG, it looks sort of like this. We have these two guys becoming collinear. And this is a universal factorization limit, which Shruti discussed at tree level. But it's also very uniform, universal at loop level too. And so we know exactly what is going on here, just based on some universal behavior. In fact, we had this formula E, which is the e to the gamma cusp over 4 times E1 plus R. And you can show that in this collinear limit, this just goes to 0. So we have very simple prediction for the leading power behavior. But you can also go to subleading power. And then in this limit at subleading power, we have much more intricate and detailed predictions that come from the OPE approach, and in this case, more specifically, something called the form factor OPE, which I mentioned at the beginning is due to Sever, Tumanoff, and Wilhelm. And so by using this information, which in fact it's enough to use the terms that are order V, and then there are logarithms, and we can use the information of a couple subleading logarithms. And after that, we get a unique answer. And then we check that answer with even further subleading logarithms when we're at high loops. And of course, all the checks work. And then in some sense we're done, except for integrating up these functions. But we've actually gotten all the way to 8 loops. And so these are 16-fold iterated integrals. So they're pretty big, and we don't even know what they are everywhere in this space. But we can find simple lines where they collapse to simpler things. For example, up here, there are only 16,000 terms in the 8-loop expression, whereas it would be, you know, tens or hundreds of millions probably if we were trying to do something that described the whole area. So after we have this unique result and we promote it to full function level, we can actually make plots and understand what's happening in this theory at very high loop order. So there's like a finite perturbative radius of convergence we can explore. There are other interesting limits we can look at too. And in view of the time, I think that will be the end up to your questions.
Okay, thank you. Any questions?
So the same basic procedure works for other kinematics. I mentioned the hexagon and heptagon cases. You just have to understand what's the right alphabet. And that's something that other people have been engaged in exploring at higher points than we have.
Can you say, are there any interesting limits in which you can sum to all loops?
Yeah, the hexagon case has a limit. And in this, this actually has this duality, which lets us map somehow to the hexagon case, but I'll talk about that next week. But the hexagon case has richer kinematics, and there, one point that's very easy to get to is this origin, and things simplify a lot there. I mean, these FFOPE limits, they're in principle known to any power of the coupling, but evaluating it, it becomes very large infinite sums, so doing it at arbitrary high order is very hard. But at this origin here, the MHV amplitude becomes roughly e to the gamma log squared, where gamma is a kind of anomalous dimension, and these are quadratic in the kinematic variables that are going to zero. So that's one nice example of something you can find, and it was mostly found just by looking at it perturbatively and seeing that everything was quadratic amazingly at that point.
Okay, because of lack of time, we have to thank Lance for the whole course again. And we go for lunch, and don't forget that after lunch, people who are interested will join Christoph and others for the tour.
Doufáme, že je lunch.